Thanks, Anna. Yes, so as Anna just said, my name is Eero. I work with the Finnish Met Institute, and my talk will be, the introduction talk to the practical, will be on sea ice thickness from altimetry. It could have said sea ice thickness from Cryosphere 2, but there are a couple of mentions to older altimeters there as well. Rachel Tilling has helped me put this together, and she'll be the second person running the practical after my talk. So most of what I have in the presentation was already said earlier today, which is great because repetition is mother of learning. So I'll repeat the stuff in a slightly different way what Louise and Sinead already told you. And at the end of the practical, you should have an understanding how we get from quite low level altimetry data into nice looking sea ice thickness maps as the one right here. So could anyone tell me what these are? Waveforms. Aye, good. You have been awake. But in the big picture, the thickness retrieval itself is not really the most important thing. Journalists will not call you and say, could you tell me about the retracker you just did? They're not going to do that. Unfortunately, I would love if they did. But instead, they will be interested in plots like this. This is made by Rachel, a time series of Arctic sea ice volume. So that's launch of Cryosphere there, 2010, all the way up to this spring in 2016. What we see there is interesting stuff. Actually, Sinead already showed you a different version of this graph, but the green triangles, actually I can just make that a bit larger. The green triangles are the volume of multi-year ice. Volume of ice that has survived at least one melt season in the Arctic. And you see the early summers here, there's a significant drop in the volume of multi-year ice, in the amount of multi-year ice in the Arctic. But then, come 2013, during that summer, the multi-year ice stays in the Arctic. It doesn't go away. There's something has changed from the year before. Similarly, from the maximum volume of last year to the maximum volume this year, there's a drop of about 10%. These are the interesting things. These are the geophysical things. These are the things that affect people's lives, not retracking. Although, having said that, you need to retrack waveforms to get the important stuff. A bit of vocabulary here. When I talk about sea ice, I talk about frozen seawater. Seawater has salt in it. In consequence, sea ice is also saline. If you lick sea ice, you will taste that, or if this is not fresh water, it's actually seawater. This is just to mention that when I talk about sea ice, I do not include icebergs, because icebergs have been carved off a glacier, and that will be something different. Quite often you'll see the abbreviation FB, not standing for Facebook in this practical, but freeboard, just the elevation difference of local sea level and the upper surface of ice. Flow is an ice flow, so as Sinead showed you in the photos, Arctic sea ice is not a uniform slab. It's smashed into pieces or flows. Flow can be, well, a couple of tens of meters wide, or it can be, well, tens of kilometers. They vary a lot in size. Lead is an ice-free area between ice flows. So a crack or a lead is the same thing. Whereas open water is, in my understanding, a big sea area with no sea ice at all in it. And it's very easy to confuse these two. So the basic idea, once again, this has been already told you today. What do altimeters measure? Anyone? Elevation. Correct. They do not measure thickness, or they do not directly measure the thing that we want. So if only we could detect the elevation measurements, just to differentiate the elevation measurements that originate from water and the elevation measurements that originate from the upper surface of ice, we could just take the difference of the two, say that's freeboard, use the Archimedes principle to calculate the thickness. And this is the basic idea. This is how we do it. Word of warning, when people say freeboard, they may either talk about the elevation difference here from water level to the snow-ice interface, or they may mean the elevation difference between water level and the snow-air interface. In my talk, it will always be from water to the ice-snow interface. Just bearing that in mind. Any good presentation should have a flowchart, really to mostly there just to keep me aware what I should be talking about. The flowchart is from the ESA Climate Change Initiative CI's documentation. It's a public document, and it's basically a cookbook how to build a CI's thickness processor. I'll ignore most of the boxes, but let's look at a couple of them in a bit more detail. The first one is the flow ocean and flow lead discrimination. Once again, we remember what Louis said about waveforms. Different surfaces result into different waveforms. Thanks, Louise, for letting me steal the slide. But leads are smooth. They return a specular echo. If you can see the range here, this is in 10 to the power of minus 14 watts. But the labor here is 14,000, whereas the maximum power in a waveform from an ice flow is in the ballpark of 5. So there's a several magnitudes difference in there. So it's not that, at least for idealized waveforms such as these, it's not a hard task to differentiate the two. What will be harder is to differentiate ocean waveforms from ice flow waveforms. What we usually do is we take an auxiliary sea ice concentration data set and only concentrate on the areas where we know ice exists. Then if we see a nice blurry diffuse waveform, we classify that to be an ice flow. There's a way to quantify how peaky the waveform is, and that's just taking the maximum power in the maximum range bin, and divide that with the integral over the whole waveform. You'll be doing that in the practical. The variable is called pulse peakiness, and traditionally with ERS RA and NVSat RA2, which were pulse limited altimeters, pulse peakiness alone was what was used to distinguish lead waveforms. Delay Doppler altimeters, so if you increase the resolution along track, this is what Noel mentioned earlier today, if you do the delay Doppler processing, you will get a side product called stack standard deviation, which is very convenient in the lead flow distinction algorithm. You can, if you want, you can make it even more complicated and define a couple of other pulse peakinesses like Robert did. Left and right pulse peakiness, just look at Robert's paper, helps you to not only to detect leads, but also to detect leads that are off nadir. What's the SICCI? SICCI, Sea Ice Climate Change Initiative. Yeah, Thanks. So after we know which waveforms come from where, we retrack the waveforms. This is from the CCI processor. And you see here, it's a different beast for retracking leads and retracking flows. We actually use a different retracker, a completely different system for the peaky waveforms and the diffuse waveforms. You don't need to do it that way. Alfred Wegener Institute people just use the same retracker for both. You can do it. Doesn't make that much difference. The bad thing about different retrackers is that they are very hard to validate. They are tools. If you go to a building site and ask one of the workers there that which one is the best screwdriver, you will definitely get an answer. Definitely they will have their favorite like we do, but it will be hard for them to actually make you convinced that yes, I can quantify the bestness of my screwdriver. Same thing with retrackers. Retrackers are mathematical descriptions from the waveform to a number where we think the scattering surface is. We use different retrackers for different things. If we want to be aware of the snow surface, we will use a different retracker than we would use when we really want to be as sure as possible that we are tracking the ice-snow interface. Quite often it's very convenient to use a retracker which will tell you if the retracking has been unsuccessful. So in addition to the number, the range bin where you think the surface is, if the retracker could return you some kind of an estimate how good the retracking was, that's very convenient. But take-home lesson there is, when it comes to retrackers, pick your poison. There are several available, or if you don't like any of them, make your own. So after the retracking, what we have is the range between the satellite and the surface we have just measured. The range is reasonably easy to convert into the elevation, but the problem there is that we measure the altitude of the satellite, of the platform, in reference to an ellipsoid, just a reference ellipsoid, which is a different thing than the actual shape of the Earth. Then when we have the elevations into something convenient, we can just take the lead detections, lead elevations, fit a line, and voila, freeboard will be the difference here. You'll be doing this in the practical, by the way. But I can't remember who it was, probably Jeanette, who said the sea is not smooth. So because of the geoid, because of the atmosphere, there are all kinds of wrinkles in the ocean, in the large scale. If you look at the scale here, it goes from minus 60 meters to plus 60 meters. And even in the Arctic, we are talking about tens of meters of elevation change in reference to the actual mean surface height in reference to the ellipsoid. We need to remove that. So if we just take the elevation we have measured with Cryosat in reference to the ellipsoid once again, we go from minus 10 meters close to the Russian coast in Siberia, and when we go close to Greenland, we are in the ballpark of plus 20 meters. These wrinkles in this areas, for example, here where we have curvature, will mess up the local sea surface height interpolation. So you need to remove the mean sea surface height from the elevations, and you need to have the measured elevation in reference to the mean sea surface height. Then you can fit a line into the lead detections and use that to calculate the actual freeboards. Then I'm glad Jeanette already talked about this. When we have the freeboard, it's easy and straightforward to calculate the actual thickness. Given that we have a good estimate for snow density, density of seawater, density of sea ice, snow depth, and all that. What we do usually have, the easy one is the density of seawater. We know that pretty well. That doesn't change that much. Unfortunately, density of sea ice does vary quite a bit. New sea ice with all the salt from the sea still inside the ice is more dense than multi-year ice. When the salt gets flushed away, some of the brine channels will remain empty, and the bulk density is, we're talking about 10% less in the multi-year ice than in the first-year ice. Thus, when we do the conversion, we should have some kind of an idea if this is first-year or multi-year ice. And there are a couple of estimates available, a couple of ice age products or ice class products, but we don't know which one of them is best, and they have a significant effect on the thickness we produce. For snow depth and density, in the Arctic we have the climatology that was mentioned before. So we use the Warren 99 climatology, which was collected over multi-year ice in the 60s, 70s, 80s, and early 90s. We know that there's a lot less multi-year ice nowadays in the Arctic than there was back then. So what is usually done is we modify the Warren climatology, just take away some of the snow when we know that the area is now covered with first-year ice. Post-processing steps, I'll just bring this back for a while. So the green dots are measured flow elevations. You see they are noisy. So with Cryosat you get about 10 centimeters of noise in one single measurement. 10 centimeters in freeboard is almost a meter in thickness. So the signal is noisy. You need to average several measurements to get something reasonable. You don't do anything with a single Cryosat elevation measurement. You need a large number of measurements, large enough number for the averaging to work. And word of warning here, so we have negative freeboards. So actually the elevation of the upper surface of ice has been below the local sea level. How does that sound? Is that reasonable? Well,
have a lot of snow.
It's not reasonable, but
yeah.
it is reality.
Yes. So yes, it happens sometimes. If we have a lot of snow, it can press the ice below water, and if it's a conveniently shaped flow, you might actually have negative freeboards that are physical. If you drill a hole through them, you get a great fountain gushing up. So that does happen, but not to this extent. So,
I was just going to add another thing, Eero. So we've removed the mean sea surface.
Yep.
And so sometimes what can happen is the actual sea surface can be below the mean sea surface. And that might be, for example, if there was a high pressure system.
Yep.
And now, of course, we are making corrections for that as well.
Yep.
But there's a little error on each of those. So, you know, due to the geophysical correction, sometimes that can cause the elevations to end up below the mean sea surface.
Yep.
So
That's true.
the reality of what we're doing here, but it does seem like negative freeboard is kind of hard to imagine.
Yeah, Stefan. Yeah.
Why not include the dynamic sea surface height?
But that's what we're doing. That's what basically we're doing. So we are measuring the dynamic actual current sea surface height from the lead. That's why we do the.
That's a measurement. That's
Yep.
actually an output of this.
Yep. Yeah. So the way to measure the dynamic sea surface is to use these exactly same measurements.
So do we get the dynamic sea surface height in ice-covered oceans? ocean as well?
Yep. Yes.
And we can calculate the ocean current from that as well.
Yes. Right, but anyway, the point I was making earlier is that the noise is large enough for the freeboards to go negative, which are unphysical in this context, but you cannot throw them away. Keep them there, because if you chop away all of the negative freeboards and then average, you will introduce a bias in your product. So do not throw good noisy measurements away. Grid the thicknesses into a convenient grid. You need a large enough number of measurements. So for Cryosat, we're talking about in the ballpark of 25 by 25 kilometers over a month or so. Beware that there are thicknesses and thicknesses out there. So for myself, when I say the average thickness in this grid cell is, say, 2 meters, that means that the average of all of my successful thickness measurements is 2 meters. It does not take into account that maybe the CI's concentration is less than 100%. Maybe there is just one flow that's 2 meters thick floating in the middle of the grid cell where we get one nice measurement saying 2 meters. That will go to the product as the mean thickness. People who do CI's modeling, usually when they say the average thickness in this grid cell is something, they mean the model thickness, which is taking all the CI's volume and spread it to an even slab. So if there's a flow that takes half of the grid cell and that's 2 meters, they will say the average thickness is 1 meter. There are thicknesses and thicknesses. When you talk to someone about CI's thickness, make sure which definition of thickness they use. Or just go the easy way and talk about volume. Volume is always volume. So, yep.
I have a question about the leads. Like, how wide are they? Because in the talk before it was like that we have an asymmetry resolution of like 200 meters or so. And if I get now a point at the ground which includes like a lead and ice out, that was the first step where I classified them into either water or ice, and then I retrack them. Or do I retrack a combined response?
You don't. Basically, you don't retrack it. You try to distinguish the mixed echoes, which you have a lot of. So there will be a lot of waveforms that originate from a mixture of leads and flows. And you try to get rid of those. You look at, all right, there's something that looks like a lead, something that looks like a flow. So ignore this, remove it from processing.
Basically, that will only leave me with leads that are over 200 meters, right?
Not necessarily, since radar altimeters are extremely sensitive to the presence of open water. So it doesn't have to fill the whole wave, whole footprint. But Tom had something to say. Yeah, once again, remember the waveforms, 14,005. So different. All right. Yeah, so just quickly mentioning a couple of sources of uncertainty. Noise is one. Preferential sampling, which is very much related to what you just said. Maybe we do not catch the small flows. Maybe we do not catch the flows that are small and thin, and filter them out from our processing. So that's a problem. Radar penetration, in all fairness, the radar signal does not always penetrate to the snow-ice interface. We like to think it does, but depending on the snow, it often does not, especially in the Antarctic waters. Ice density and snow are both approximations. Snow and ice, snow load, including density and thickness, and ice density are the biggest individual uncertainty. sources in the processing. It works only in the winter because in the winter we presume that the snow is dry. We get the penetration all the way down to the ice-snow interface. In addition, in the winter, you will have melt ponds. You will have water on top of the snow, and that will mix your lead detection algorithms. So we only use winter data. Validation. Rachel told me to put in a pretty picture about validation work here. I'm sure this was not what she meant, but this is a plot from Seymour Laxon's last paper. The point I want to make here is that this is from airborne electromagnetic measurements. This is from a mooring that was left under the ice for several winters, and this is Operation Icebridge. Again, airborne stuff. You can't validate cryosat by drilling a hole in the ice. You will need to drill a hole in the ice to calibrate EM, for example, so you need to go up there and do the work. But you need something that covers a lot more area and a lot more time than just field measurements when you validate the thicknesses. What about the south? No thickness estimates there from altimetry yet, mostly due to the fact that we do not have even the snow climatology we have in the Arctic. So in the south, there's no climatology because there has not been Russian floating stations for the past 70 years doing the measurements. If someone would know of a good source to get the snow estimate on top of Antarctic sea ice, please talk to Robert or myself. We'd be much interested in that. And that's also, I like the plot because this shows the difference between cryosat and an older altimeter with a bit more coarse resolution. And with the radar altimeter 2 on the right, we seem to be losing the thickest ice and the thinnest ice, but cryosat catches it better. Right, how much time do I have? I'm already running late. So if someone wants to really get into the sea ice thickness processing, Google a package called PySerial. It's a Python package that does pre-processing, all of the mean sea surface height thing, retracking, gridding, open source, made at Alfred Wegener Institute. Very nice. Further reading, you don't need to go through those now. You can just, when you get the slides in the end, if you're interested, look into those. So, the practical, the interesting bit that you're going to do now, we're going to go up to the computer lab. You'll be using MATLAB. Hands up who has used MATLAB before? Oh, yes, good, good. There will be two independent parts in the practical. One of them will be taking UCL processed thickness products and working with them, just looking at them, looking at changes in ice thickness, etc. The other part is a lot more technical, beginning with level 1B waveform data and building a simple freeboard processor. So I hope you guys will enjoy those. And it will be me, Rachel, and Tom. Could you, Tom and Rachel? You'll be the teachers, right? Yep, so these people.